Now to the naive Bayes classifier. And we're gonna have a lot of spam, or no, we're gonna classify a lot of spam with naive Bayes classifier, which is extremely successful at this, or it was so until recently, when everything is handled by deep learning. But still, a very nice, very understandable model that will help us to, uh, or like that our knowledge that we gathered or accumulated so far will help us to understand really easily. So, detector for spam filtering, this is your project. Say you need to detect whether an incoming message is a spam, and all you have is some features: date, time, recipient path, IP number, sender, encoding, many more features. Or, as we'll see later, you can just use the full text of the message without all of those features. But now assume that some features are there. And for every incoming message, we need to quickly say whether it's a spam or not. How do we do that? Let's make a few assumptions. Let's make that all of those features in a spam email are conditionally independent given the class label y. So let's say presence, I don't know, the time of the day when the email came is independent of the length of the email if we know the class. And if we make that assumption, we then see our familiar conditional independence of our features. So this is feature y, feature I, and it could have multiple values, and feature j, it would have multiple values of its own. But the class y is, once it's fixed, those features are independent of each other. And we've seen that examples in the beginning of this lecture, in the beginning of the last lecture, I think, on the maximum a posteriori. Oh no, that was Emily. Yeah, in the beginning of Emily section, you've seen a lot of examples of conditional independence, or quite a few at least. So in this case, for multiple features, we can represent this conditional joint probability of those features. And those are all features that we will decide to use to detect our spam. They could have different values depending on the values that they have. They uh, could have, like, they would have different probability. So this probability distribution, um, conditional probability, would say what is the probability of xi having some value given the class, given the class, say no spam or spam. What is the probability of date being greater than certain date, or the time of the day being either morning or afternoon or noon or evening. Like for each of them, this will be our probability with the feature value, right? So we need to be able to evaluate this probability distribution. Plug it in here, uh, say plug in morning for the time of the day that the email came in, and this particular time of the day probability, conditional probability distribution should return us some value. And then we go to the next feature, plug it in, and we'll get another value. So we can estimate likelihoods independently at each point. And also, by the way, we can have the priors as well here. We can have Yeah, we can represent our joint probability distribution, so they are jointly independent, but we can represent joint probability distribution, and then it will be this will get it. So now imagine that our numbers are either in or out, either present or not. So X is a binary vector where each position encodes presence or absence of a feature. And so Y and also Y has X classes. So X is binary. So each Xi is either 0 or 1. How many parameters do we need to estimate if we are to model this probability distribution, right? So for a binary vector, we need to estimate probability of those parameters will be probability of each possible settings of those X given Y. So for a binary variable, it's 2 to the D number, the length of those features. Well, -1 for the degrees of freedom, because if we know probabilities of everything but the last element, we can compute the probability of the last element as the sum of all of those probabilities, well, as 1 minus the sum of all of those probabilities. But then we need this kind of distribution for each value of of class. So that's why we're multiplying by the class. And that is if we don't use this conditional independence assumption. But if we use this conditional independence assumption, we only need d times k variables. Compare 2 power d times k versus d times k. Huge savings in number of parameters to estimate. So this number of parameters to estimate reminds us of the curse of dimensionality. And yeah, that's basically it. When we're in a binary space, we're in a binary hypercube and just need to estimate those uh, corners of that hypercube. For each of the corner of that hypercube, we need to estimate the parameter, and there are 2 power d of those. Once the important part is once we made that assumption and represented our class conditional distribution, the conditioned on class, as a product of class conditional distributions for each feature, we're free to choose any form of likelihood and prior that fits the job, right? We could, again, I remind you, we could have a prior here, and we could choose any functional form here that we would like. So here's how the classifier would work. We have a class prior, and then D conditionally independent features given the class label. Given the class label, they are supposed to be, or we need to assume that they're conditionally independent. And for each feature, for each feature I, we have conditional likelihood probability of xi given y. In this case, our decision rule for our naive Bayes classifier will be the following. It's argmax, so return of y for which this product is maximized. Class conditional likelihood of the features times the prior, or with naive Bayes decomposition, it's a product of all individual feature class conditional distributions times the prior, and this returns as the most likely class. A class that maximizes maximizes this joint probability of the observed feature and the class, because this here is nothing but xi, well, 1 through d, comma y. So from this, you already can see the advantages and problems, right? Well, I hope you do um, from here. So the advantages, as I already said, exponential improvement, exponential decrease in the number of parameters to estimate. The problem immediately here, we're dealing with very small numbers, and we're taking a product of a lot of features. If we have lots of features, then it will be very hard to deal with this quantity. But of course, we know to always take a log and still maximize this um, and get the same solution. So this one is easy. But let's see what else can we do, or what else happens. So the naive Bayes for discrete features, just as an example. Imagine that we have a set of training data, an example and a label, and this is a sample index in our data set. And each sample is a feature set, x1 through xd, number of features. So n d-dimensional features plus class labels, where n is the size of our data set. And we have our decision function for naive Bayes, which is maximizing our joint distribution of labels and labels and features, but in effect, it's maximizing the posterior, as you remember from the first part of this lecture, because what's written there is nothing but probability of y. When we maximize this, probability of y given all x's is proportional to this posterior. Basically, it's a posterior distribution when we're maximizing it, or naive Bayes maximizes, gives us a maximum a posteriori estimate of the class. So for discrete random variables, we can estimate everything just using maximum likelihood estimation. So individually, we can estimate the values using maximum likelihood, but then we can apply those estimated prior and conditional in a Bayesian way. So class prior will be estimated simply among all of our data samples. How many times does this class come up? So for example, if class y equals 0 comes up 100 times out of 1,000, so we can just count all of the documents, look at the y, like go through all of the all of the j samples, look at which ones are class 0, and just count those. That's what this is. That's how we will estimate the prior. For the conditional, we will just estimate the joint and normalize by the prior. Estimating the joint is also simple. Go through all of the documents, and at each document of class Y, say 0, look at the value of feature I. And if that value equals, say again, if all features are binary, we will have what's the count, how many times this feature is 0 and how many times this feature is 1 for this class. So we will count this and normalize by the number of total instances, and then we will divide by prior on y that we already estimated here, and that's how we'll get and that's how we will get our parameter estimates for um, those discrete features. Okay, that I hope that's clear. The notation here is a little bit confusing, but it's precise, so that's good. So basically, just look at the co-occurrence, count co-occurrence, and normalize to get the conditional. Uh, one thing, one thing to note. No, okay, we will come back to what to watch out for in this case. In this case, but the important lesson from this slide, at least, um, if you want to work with naive Bayes classifier, first you need a training data set, and the training process of naive Bayes classifier is estimating those distribution functions. For discrete variables, the estimation is just getting the counts, just getting the frequencies, basically, because that's the choice. You went with multinomial distributions, and that's just the counts. Imagine it's a six-sided die. You throw it, you roll it multiple times, and then out of all of the rolls, you just count how many times six came up. Right? And then normalized by the total number of times. So that will be how you calculate the classes. But then some other features are there, so you estimate them differently. For example, let's look at a concrete example: text classification. We may want to classify email as spam, not spam, and I will show you how to do that, or how it's easily done. Um, Other ways, more precise, but we're not going to touch those. Example two, classify articles into topics. So what are our features X in this case? Well, let's just use the complete text of each email, for example, each email or each article. How do we do that? Well, first, let's do it naively. And pun is actually not intended, but anyways. So let's fix max length of an article or an email and encode each position as x1 through 1000. So imagine we will chop all of our articles or of our emails by 1000 words and encode each position as this vector. So x1 is word at the first position, x2 is word which word is at the second position, and x1000 is word is at 1000 position. Since we want to allow shorter emails, we will add to our vocabulary a no word, lack of a word. So xi is a word, and that's what I explained, but xi can take any value from 0 to d, where d is the size of the vocabulary or dictionary. Say we have total of 50,000 words, but it could be easily 100,000 for an typical English dictionary. Then probability of x given y will be large, like the parameter space. To parameterize that, we will need to estimate, in this case, if we go with the joint probability, we need to estimate k times d power 1000, where d is the size of our vocabulary and k is the number of classes. Well, for spam, non-spam, it's just 2. For topics and categories for articles, there could be many, around 10, say. Well, a very large number of parameters, so we will need astronomically huge data set to even like have each parameter instantiated. So instead of doing that, naive Bayes to the rescue. So what would naive Bayes do? As you know, we can just represent probability of class given each word or each position, actually. Probability of word J at position I for class Y. Yes. And I'm now overloading that J symbol. It's not sample anymore. J now is one of the words in vocabulary. So if our vocabulary is 50,000 words, we need to estimate 50,000 times d times 1,000 parameters for naive Bayes because what are we estimating? Oh, okay, that's a typo. That should be k, number of classes. Yeah, d times k exactly. Let me think. Yes, so each of the conditionals for each of the features, given a single class, we have 50,000 parameters to estimate because that is the number of values this word at this position can take. And then we have k classes. So for each of them, we need to estimate this, and then we need to do it for each position of for each position in the email. That's better, much better than this monster, but still not quite good. It's a lot of parameters to estimate. So let's make another assumption. Let's sort of silly assume that word order and positions don't matter, only presence. That with text, and especially with our speech and our communication, the order always matters, right? At least on a long term, but it complicates the things. So let's assume the order of words don't matter. Like doesn't matter what the words how they are arranged within the email. We only look at the presence. If a word in the dictionary is present or not. So our vocabulary or dictionary is 50,000 and x is a binary vector. So we take an email and for each of the word in this email, we flip a bit uh, in this binary vector. If a word is present in this binary vector, the bit will be on, and for those words that are not within this binary vector, it will be off. So now we have 50,000 dimensional feature vector for each email, and it's mostly sparse. We just now need to estimate 50,000 times k parameters. D is binary, and then the in this case for the degree of freedom 2 minus 1. So that's what we have. Kind of silly assumption, but works really well in practice for spam and email classification. Gets to accuracies of 86 and above percent. The first successful spam filters were built like that using this bag of words model against tracing bag of words because we just take coherent, linearly organized, ordered text and throw it in a bag and toss, mix and create a mess of the words. But it doesn't matter because all we're looking at is whether a word is present or not in this text. So there is a problem with this whole approach with the Bayesian naive Bayes classifier because what if you never see some particular value for some feature and some class? What if in the training data set some combination is never present, which is not surprising. For example, if we never in our training data set see word luxury for no spam class, So imagine in our training data set, no one used that word in a normal email. It was only seen in the spam email. So if that is the case, then probability of seeing luxury bit in this vocabulary length word feature vector, probability of seeing it 1 together with no spam class is 0. Using the naive based assumption, we're saying that probability of seeing word luxury given the class spam is also 0. And in this case, see what happens. In that case, we have this joint distribution of all of the features in our likelihood, and we decompose it using our naive Bayes assumption of conditional independence. And look, we never seen this as a training data. So this is always 0. So no matter what the values are, just because we have not seen this particular combination of this feature and this class, all of our predictions will be 0. All of our probabilities will be 0. So we will never count for anything for this class no spam. So now what? Well, there are a few ways to address that, and one way is called Laplacian smoothing. Basically, when we do the counts, we artificially add 1 for each possible feature combination. So for all of the possible features given a class, or not possible feature combination, feature value. So even if we don't see this in our training data set, we still add 1 to the count and say if we had, without this Laplacian smoothing for a binary variable, if we had, I don't know, let's call probability like count of ones would be count of zeros plus count of ones for a binary variable. But then what we do by adding 1 to each of the features, like all of our counters initialized to 1 initially, and we are just correcting our estimates by this factor because we added 1 to this and to that from the start. In a multi-category case, it will be sort of cardinality of our variable number of possible values. That's called Laplacian smoothing. Doesn't improve our estimates, but at least allows catastrophic collapsing of everything to 0. Allows to avoid catastrophic collapsing of everything to 0, sorry. Yep, okay. We can classify text using bag of words now. We can minimize the number of parameters to estimate by using naive Bayes assumption. Very simple classifier, very simple estimate, just compute the counts from the training data. And what are the other properties? Yes, the counts seem confusing, right? But it's a consequence of our choice of the likelihood and prior. We can choose anything we want and estimate those probabilities, the likelihood and prior, as appropriate for our choice. So yeah, notice naive Bayes classifier only governs the form of conditionally independent maximum a posteriori estimate. What is P of y? What is probability of xi given y? Is your choice. And you decide depending on the difficulty of the problem, as you will see in a micro project in your homework. So conveniently estimated everything relatively to individual points. Yes, that becomes really easy compared to estimating a joint feature space. We just work with one feature at a time and just watch out for empty labeled feature combinations in the data. Use Laplacian smoothing. This product is also product of numbers of less than one is killing us because the larger the larger the number of features, that means the smaller individual values. We just use log probabilities instead. That's naive Bayes, but what if the features are continuous? What do we do then? Can we use naive Bayes, or naive Bayes is only good for discrete features and for spam filtering? Well, as I said, likelihood and prior in naive Bayes could be of your choosing, and you can just modify according to the task. So for character recognition, like in this MNIST character set, we can take our features to be pixel intensities at each point, and then use Gaussian distribution for the class. For each pixel would be now probability would be modeled as a Gaussian, and depending on the class. So for each class, it's a different Gaussian with different parameters, and we can feed those parameters for each class, each pixel. So 10 classes, 700 and something plus pixels. That will be our product of the pixels. So as I said, 700 something, and probability of that pixel, continuous value of that pixel given class will be modeled as a Gaussian distribution. And again, just look at your data set and individually consider each pixel in each of this image as the samples and fit a Gaussian. You already know how to compute maximum likelihood estimate of. To simplify our life, in this case for each pixel, we can sometimes assume that a variance is independent of the class or is independent of the feature, just so we can estimate the variance based on the full data set regardless. Or we can just assume the variance is independent both of the class and the feature and estimate the variance just jumping together all pixels as a one-dimensional distribution. Okay, that's how we can classify those pixels, and the accuracy I believe will be around for MNIST will be around 86%. Can you imagine? Yes, with convolutional neural network you can quickly get way above 90, but that simple Gaussian distribution, one-dimensional Gaussian, that's all we have here, and we're getting to super good baseline, surprisingly. Okay, but what do we do with more complex data? Let's classify mental states. Also possible with this simple maximum a posteriori assumption and conditional independence. So let's take brain with resolution around cubic millimeter, one image per 2 seconds, about 15,000 voxels per frame. Voxel is a three-dimensional pixel, and containing gray values, same as the images here. So non-invasive, safe, measures blood oxygenation level dependent response, hemoglobin concentration. You can think about it that way. So if we do that, then we can get to accuracy of predicting brain activity based on word category of what a person sees. A person is demonstrated um, an image of some object from the category, and the algorithm needs to predict from the brain activity just from voxels. Each voxel is assumed conditionally independent from the other, the same way we did for MNIST. And the accuracy on 12 participants gets from 80 to 100%, surprisingly. Well, maybe not anymore, but such a simple method and such a good result. Nice. That concludes our naive Bayes exploration. I hope that's fun and clear. We'll come back to um, some useful tools for further work with naive Bayes, because you need to be able. Well, one thing to internalize is you are the one who is controlling the shape and the functional form of the likelihood and the prior. So you choose it wisely depending on what your problem needs and depending on how easy it will be to estimate and deal with. But if it's continuous, if the random variables are continuous, you can always either go with some parametric form like Gaussian and estimate it from the data for each pixel voxel, or you can go with non-parametric form, which is a topic of one of the next lectures. And then you still can use a naive Bayes decision rule and select a class predictor. And non-parametric estimates are not so bad. Okay, until next lecture.